We've identified our Newton's pair. There's only one. Now let's look at see if you can rank the magnitudes of the horizontal forces. Where are we? So where are we? These are the horizontal forces. 1, 2, 3, 4, 5. 5 of them. We identified 5 horizontal forces. A pushing on B. Remember, this is our situation. We're pushing on block A. Block A is pushing on block B. The whole thing is moving to the right at constant speed. And we identified 5 horizontal forces. Block B pushing on block A pushing on block B, the force of a hand or something pushing it, a friction force on B and a friction force on A. Those are both with the ground. Okay, those are our 5 horizontal forces. What can we say about those? The Newton's pair, we know those are equal, right? With what? They're to each other, the 2 friction forces to each other? We don't know enough yet to compare those. How are the blocks moving? Constant speed. So there's no acceleration. If there's no acceleration, then there can be no net force on the block because that's what causes acceleration. So we can look at the blocks individually because both of them are moving with constant speed. And we can look at them as a unit because as a unit they're moving with constant speed. So let's take a look at, so first we've got a Newton's pair, right? Normal force AB equals normal force BA. We've already talked about that one. Now let's look at no acceleration. So that tells us the net force has to be 0. That's a vector equation, right? When we add up the vectors, we have to get 0. So we can apply that to block A. The net force, another way of writing that is this way, using the sigma, the sum of all the forces. That sigma means sum. The sum of all the forces on block A is, what is it? What we have to define a direction as positive. Most of us like to the right as being positive, so I'll pick that. To the right is positive. So we have a force to the right on block A, and that was this push, F push. And we have 2 forces to the left. So I'll write it in here, F push. That's positive direction minus the friction force on A from the ground minus the normal force on A from block B. And I'm not going to put vector hats on those because I'm taking the direction into account with those minus signs. So these are just the magnitudes now I would put in here. Okay? The direction so those take care of the direction, and I just put magnitudes in for the values now of those forces. What do we know about this? It has to be, I'm going to move this somewhere else, sorry. It has to be equal to 0. That's what no acceleration means. To the right is positive. Okay, so that's for block A. For block B, the net force, another way of writing it, the sum of all the forces acting on B. I'll use to the right as positive again. Where's B? We only have two forces. We have a normal force, A, pushing on B to the right, and a friction force to the left. Normal force on B due to A, it's positive. And we have in the negative direction the friction force on B due to the ground. Those are the only two forces they have to add to be 0 because there's no acceleration. Block B is moving at constant speed in a straight line. All right, let's see what we can conclude from all of this. We've got a normal force on A from B equaling the normal force on B from A equaling the friction force on B from the ground. Those are 3 of our 5. What do we know about the last 2? The friction force on A. We haven't talked about friction forces yet, but well, let's just think about it for a second. We've got a block B, and we're pushing it, and it's interacting with the surface that it's sliding across, right? There's an interaction there, a rubbing that takes place there that creates a force opposite its motion. And we have another block that's twice as massive, it's equal to 2 of the other ones stacked on top of each other, and we're pushing it, and it's interacting with the surface and rubbing across that surface. Which one do you think might have, would the friction forces be the same? Would one of them have a bigger friction force, do you think? The bigger, heavier one, right? Because as it rubs across the surface, there's the bigger, heavier one has a bigger force of gravity pulling it against the surface, and so that it's going to rub harder on the surface, right? It actually depends on the normal force. But in this case, because it's a horizontal surface and there are no other forces acting on it, the normal force just equals the weight of gravity. So the bigger, heavier one is being sort of pulled into the surface, pressed into the surface harder. So as it tries to rub across the surface, it interacts more with the surface and is hindered. Its motion is hindered more. There's a bigger friction force on the more massive one because it has a larger normal force. Okay? We'll get to that. So that means it's going to end up on this side. Friction force on A to the ground is going to be greater than those. And that leaves one more. What do we know about that one? The force that we're pushing with. What is this equation on the up above on the top there? The net force on block A, the push force is equal to what? going to equal the friction force plus the normal force on A from B, right?